I'm going to like make an observation, which is, why did I only go from 0 to 90 degrees? It's not like that's the only possible, any two vectors are at angle between 0 and 90 degrees. It's true that all the examples we saw before were between 0 and 90 degrees, but they could be at like 110 degrees or something. They could be at 170 degrees. They could also be at like, well, in some sense, like maybe you should measure the angle between two vectors between negative 180 and 180. And actually, it doesn't really matter if it's positive or negative, because it's sort of symmetric. I mean, just the angle only says, like, oh, is it like curving clockwise or curving counterclockwise? But anyway, let's plot it between, 180 degrees and negative 180 degrees. So this is pi, it's 180 degrees. And we'll also extend it back here to, what's about negative pi. Okay, and this is truly, I suppose, all the possible angles between two vectors. And if we continue the plot, it goes like this. And it goes again like this. Like that. Okay, so this is the whole plot. And now, let's think about this, because maybe some mildly interesting things we can say here. So first of all, one thing that's maybe no surprise is it's symmetric between, I mean, I drew it poorly, but it's symmetric between flipping between positive and negative theta. Like the success probability or the failure probability is the same for theta as it is for minus theta. And that's not surprising, because it's sort of fundamentally the same problem. Right, the only difference between negative 30 degrees and 30 degrees is, which side it's on between yes or no, clockwise or counterclockwise, but that doesn't really change the problem. But actually, let's even pick like, just to like make sure we are on top of things here, let's pick like, I don't know, this spot that's like 110 degrees. So the failure probability is pretty small. So why is that? I mean, maybe this is like, V, where's 110 degrees? Maybe it'd be like, this is like 110 degrees W, call it W prime. And yeah, you do have a good success probability here, because again, you could, take this to be one measurement axis, and the other one would be pretty close to V. So that's a good success probability. But kind of intriguing, the failure probability goes back up to 100% at angle plus or minus pi, which is plus or minus 180 degrees. So that's like saying, okay, if the two vectors were like, V and literally negative of V, this is saying you can't succeed at all. It's like equally bad as the case where like V and W were on top of each other, which, we talked about, well, if V and W are on top of each other, you need one-sided error, you can't succeed at all. And this situation where they're like negatives to each other is equally bad. And let me write that for emphasis. Like no algorithm can distinguish at all V and negative V. And like, if you didn't spend much time with quantum, that might seem very surprising to you. You're like, look at the picture. Like V and negative V are literally opposites of each other. They should be like super easy to distinguish, right? But no, not right. Like this is, for example, saying like, if I give you like ket 0 or minus ket 0, there's nothing you can do. You're really screwed. And maybe now you see that's kind of believable, right? Because like, let's say I give you ket 0 or minus ket 0. You could like, I don't know, do you extract? You could like measure. But in this case, you see outcome 0 with probability 1 squared, which is 1. In this case, you see outcome 0 with probability negative 1 squared, which is also 1. So you don't tell any difference between these two cases. And in fact, this is also going to sound maybe a little bit weird, but these are the same state. So what do I mean by this? Well, first of all, remember when we were talking about like unnormalized states? And we were like, we're kind of chill now. Like, the sum of the squares of the amplitudes doesn't have to be 1. It's okay if you multiply like all the amplitudes by 2 or square root of half or whatever. That's fine. These are considered the same states. Just like with fractions, if you multiply the numerator and the denominator by the same number, it's the same fraction. Well, I kind of slipped a little one by you. Like, nobody actually asked about it. But this is also true if you multiply them by the same number and that number is negative 1. So just like in fractions, like 2/3 is the same as negative 2 over negative 3. If you take a state like a plus, a ket 0 plus b ket 1, and you're like, let me change it to negative a on ket 0 and negative b on ket 1. It's like multiplying all the amplitudes by negative 1. This is also the same state. And this fact sometimes goes by like a name, which I'll say to you, even though we're not going to talk about it that much, but just in case you ever encountered this phrase. It goes by this name like a global phase does not matter. Okay, so the word phase means complex number with absolute value 1. But in this course, we're not like talking about complex numbers. So the only complex number of absolute value 1, well, there's two numbers with absolute value 1, 1 and negative 1. So for us, maybe we just say the global sign doesn't matter. Okay? Which means, it's like what it's saying is if you have a state and like you multiply all the amplitudes by negative 1, it doesn't change anything. And philosophically, actually, what's going on is, if you're like doing experiments and like you have a qubit and like it's in like this state, there's no physical experiment you could ever do that could tell the difference between it being in this state and this state. So actually, if you're like a mathematical physicist trying to model quantum states, what you should really, really, really do is choose mathematical notation under which these two states have like the same mathematical expression. And that's not what happened here. And really, so this is really just like a small infelicity in how a mathematical physicist chose to mathematize like quantum states. In some sense, like the real nature of one qubit state is it's like defined by a line through the origin, not like a vector. Like somehow, like this line is the real quantum state. But at some point they were like, yeah, but we have this great notation for vectors. We got linear algebra. It's like so great. We don't have like an equivalently awesome, like convenient notation for like lines. So they're like, you know what? Let's just use the notation for vectors for states, and we'll just like always remember this in the back of our heads, which is that there's no physical way to tell the difference between this state and this state. So I bring this up also because it can be like a little bit confusing, and my recommendation to you is to like don't like try to rely on this too much. Like if you're ever confused, just act as though these could be different states, and then just be like mildly surprised when you notice that there's no algorithm that can tell the difference. You can just be like, that's weird. Yeah, so I bring this up because you might like encounter it, but maybe the takeaway is, don't worry about it. Just let's keep doing like amplitudes like we did before, and just don't be surprised if you at some point realize things like, oh, there's no measurement that can tell the difference between this and this. Yeah. This is a very good point. Okay, since we're here, let me say this. So the point was that, like, here's a fallacious thing that you could say, and I just caution you against it. And this is why I kind of recommend, like, don't try to exploit this fact too hard, because you might accidentally make mistakes. So even it comes up more frequently when you have a 2-qubit state, this fallacy I'm about to say, but I think I can even illustrate it with a 1-qubit state. You could say I get into this state, maybe even by some little algorithm that starts at 0 and then B somehow, and this is 0 and this is 1, and you're like, okay, I did this little algorithm and I got to this state. And what I could say is you could say fallaciously oh, hey, I was told that 1 is the same thing as negative of 1. And therefore, I could have called this A amplitude on 0 and negative B amplitude on 1. And therefore, this is also the same as this, right? That's a fallacy. So that would be saying, well, these two states are reflections through the horizontal axis. So that would be saying that this W is the same as this W. And that's not true. These are distinguishable. They're not the same. So basically, to guard against this fallacy, all I can say is if you have a one state, it is true that if you multiply by all the amplitudes by -1, it doesn't change the state, or you can't distinguish these results. But you shouldn't do that to pieces of the state. Or if you have a unitary, a rotation, A, B, negative B, A, you can't say oh, I'm going to change the signs on this one, but not on this one. So this is a fundamentally different unitary. You're not allowed to do that. One thing you can do is you can do this. You can put negative, or you can change the signs on both of them, and that's the same unitary. But you might now be sitting there saying, I'm a little bit confused. What is allowed? What's not allowed? For simplicity, just pretend that nothing is allowed. None of these are allowed if you want. Just do everything carefully. Don't try to unnormalize the state or spontaneously switch the sign. Don't do that unless you become really experienced. But I'm just warning you that this is a true principle that you can elucidate that can sometimes help you recognize maybe why two things you thought intuitively might be distinguishable aren't. Okay, so I had to sort of bring up this mildly discussed, confusing topic, but we'll just leave it at that. I should also mention that there's a more advanced quantum notation that they eventually spring on you later, where this little bug goes away, and there's a unique perfect, one natural perfect mathematical expression for all quantum states where this and its negation get the same mathematical expression. But we don't really need it, so we're not going to use it. We're just going to live with this minor weirdness.